Good day to all. Today we are going to discuss with you the hydraulic similarity and dimensional analysis. So this topic is regarding the fluid dynamics and fluid mechanics. In previous classes, we have already discussed the fluid flow, Bernoulli equation, pressure drop calculations, continuity equation, or with the other name, law of continuity, and also pressure drop calculations for laminar and turbulent flow regimes. So this time we are going through and review the hydraulic similarity and dimension analysis. This will be the last topic of the fluid mechanics lessons. So first of all, we'll go through the reviewing the theoretical parts. It will be definitely actually the theoretical parts, but we may have some practical sides to discuss the general topic. In general, this is more about the geometric equations and polynomial exponents. If you are good at math, it will be very easy for you. So let's start with the theoretical part. Newton's law of motion, which says that force equals mass times acceleration, F is equal to m multiplied by ma, can be applied to moving fluids as well. So in high school, if you remember that we were discussing this equation, Newton's law of motion, it was mainly about applicable to the bodies which are in the inertia. So, but it could be also applicable to the moving fluids as well. Instead of considering the general case when acceleration is present, here we deal with the stationary case only. So when fluid moves with constant speed, in this time, additionally, we are also considering that our u speed of the fluid or velocity of the fluid, let's say, it's constant. So no acceleration occurs when the algebraic sum of all forces acting on the fluid is zero. So the forces to be counted are inertia of the moving fluid, the pressing force, the second one, counter-interacting friction, gravity if present, direction of the flow, and other terms. All of these terms, actually, they have an impact on the fluid flow, unit volumes, the formulations, the other stuff. So let's see the variables which they could be affected. First of all, you see this one, the second delta P, third one eta dux over dz, rho gh. So if you are not aware what is eta that we can already solve, for example, mu, it's also the viscosity factor, dynamic viscosity. In this book, this is actually called as eta. So for general case, dux over dz can be considered by a ratio of u. So for example, it will be the body. Let's say you have a body. It will be moving in constant, let's say the speed u across the x axis. And you have the general, the z, its direction. It will be dux over dz. So actually, if you remember the Newtonian and non-Newtonian fluids, we were discussing the dux over dz and also considering its viscosity values. So next one. Two flows in two different arrangements can be considered similar if the ratios of these members are equal. So there are three important, actually more than three, but we'll discuss here only the three of them. Very important numbers. They are discussed in the fluid dynamics and fluid mechanics. So I will show with the red color. The first one is Reynolds number. Reynolds number, as we discussed, this is just rho ud over eta. Eta is dynamic viscosity. D is diameter of your body, of your moving fluid. U is the speed or velocity. Rho is the density of your fluid. So in general, it's equal to inertia forces over the friction forces, just to keep in mind this one. So also you can write this equation in such a way that your eta over rho is equal to nu, which is the kinematic viscosity, and the second equation is also be given here. So just keep in mind one more thing, that in the description of the problem, you may see that the viscosity is given in terms of the kinematic viscosity, centistrokes, and additionally, you are given with the rho values. So you shouldn't be confused with these values. Secondly, you have the Euler number, the second one. Euler number is just the pressure over the inertia. You need to keep in mind these equations because we'll use in a moment all of these equations. The last one is the Froude number. The Froude number is equal to inertia over the gravity. So the gravity, you can see that gravity acceleration, and this is very easy to remember in such way. So we'll use the three dimensional rules. For example, we can use that fxyz, xyz, which it will be providing us the dimensions value. And in this term, we'll also consider the polynomial form with the variables. So our main variables will be, so that's what we have discussed through the other lectures, that delta P, which this is the friction factor, U is the velocity, D is the diameter, eta is the, again, dynamic viscosity, rho density, G acceleration, gravitational acceleration. Also, the length is very important. Just look at this pi value in Russian. Pi is a kind of dimensional expression. At the end of all these calculations and story, we need to get just this pi value as 1, as you can see. So you set this value. So instead of delta P, what we can write it? So delta P is what? F, which is the force, over area, cross-sectional area of the body, right? What I can write instead of dimension analysis, I will write its unit in terms of mass over L length multiplied by T square. T is just time here. So if you can derive this equation and open up with the units, you will get kilogram per meter multiplied by second square. Okay, and this is expressed in this way. Secondly, we have the U velocity. I can write meter per second. It means that meter is length, second is time, right? Then this is the same for the remaining ones. Now we are going to the mass side. So as you can see, we have the M's. We have M here, M. Then we have the L length and also the times. So let's first of all write for the M. As you can see, M is here on the numerator. Therefore, it will be just plus M. Next, we have here again in the numerator D, and we have M here as E, right? In order to get this as 1, all of them should be equal to 0. All of these expressions, A, B, C, D, E, F, H, should be equal to 0, right? Therefore, I will write A plus D plus E, it should be equal to 0. I will write the same things for the remaining ones. So, for example, let's write for the L length. So the length here, it's in the denominator. Therefore, I will write as a minus A. So then plus C, then minus D, minus 3E. Then I have here, okay, I wrote it. Yes, plus F and plus H. It should be also equal to 0. And the last one will be time, T. Let me write it like L. And we have, sorry, this is T time, minus 2A, minus B, minus D, and minus 2F. At this point, you may also stop the recording and you can write just by yourself, and then you can check your answers with mine. So all of these equations will be very helpful in order to find out what is the B, what is the E, or the other terms, okay? So for example, they have expressed the B and E from time and mass perspective. So the B, it will be equal to, just from this equation, or you may also find out with the L, but it will take long time, I would say. And also E equal to, for example, minus A over subtracting just D. So you can use this ones, and we'll also write it and put the same values into the equation again. So C is also expressed. So the pi, that's equal to delta P, A, U, that we have it just expressed, D we expressed, eta, rho, G, L. All of them are staying the same. So just keep in mind one thing. We are trying to always bring our equation or rearranging our equation in such a way that we can use the Euler number Froude number, and Reynolds number.